Okay, hi everyone. Welcome to this week's BTPC IDEA Seminar. So I'm very happy to introduce one of the BTPC postdocs today, David Ramirez. He's going to be talking about some models for classical chaos, talking about phase space, and then making some connections to quantum theories of chaos. So take it away, David.
Great, thanks, Stephen. So let me share iPad screen here. This will be a chalk talk. Right. So we're going to talk about chaos today. As you might guess, in particular, I'm going to focus on classical. I just got finished teaching classical mechanics, so I guess my mind is it's a little classical these days. But I think the overall kind of framework that I'm going to talk about is not specific necessarily to say chaos in a kind of classical mechanics Hamiltonian setting, though that will be the example I'll be focusing on primarily. So chaos is really just kind of a term for kind of a general features of dynamical systems that could be evolving under some Hamiltonian, or it could be evolving under some stochastic noise, or all kinds of various settings, quantum mechanics, etc. And so the I think the big picture of the strategy we're gonna talk about today is going to be relevant for all of these other just generic dynamical systems, and so we're going to start with classical focus, but framework more general. And so I think there are a couple of kind of main takeaways I want to emphasize. I think kind of one of the morals, say moral one, is going to be, if you want to think of it in terms of a slogan, it's think globally, act locally. Okay, so it's not super accurate description, but really what I mean here is that there is I think one of the hallmarks that characterizes chaos is a kind of robust interplay between what you could call kind of a local instability and global mixing. And so I think this local instability is pretty famous in kind of chaos context. By this local instability is roughly what we mean when we talk about things like the butterfly effect, or kind of, one of the hallmarks of chaos is that if I have two initially close trajectories, so two initial starting points that are close together, then they kind of diverge exponentially in time with some exponent that we call the Lyapunov exponent. And so I think this first part you think about. Not good at spelling Lyapunov. So this first part, this instability part, is really the kind of exponential separation of nearby trajectories. But I think really it's an important part of chaos that it's not just that trajectories separate, but they also come back together kind of infinitely many times, so that there's mixing, right? There's ergodicity, and so it's really, the slogan here is kind of ergodicity. I think there's maybe a little bit of a chicken and egg story of, maybe you might worry this is slightly circular definition in terms of defining, ergodicity is probably defined best in terms of chaos. but here, okay, this is more just for slogan purposes. But the idea is that yes, trajectories that are initially nearby will separate, but they also come back together after some amount of time. And so I think it's really that we need kind of both of these features in order to honestly say that a system is kind of chaotic. And so I should say that, I should really make a lot of caveats here. So, first, there are many approaches to chaos. It's an old subject. So this is only going to be, one approach, and I think this kind of story I'm going to tell you about, this kind of periodic orbit theory, probably somewhere kind of 70s to 90s, I would say, is where it really got fleshed out and kind of understood concretely. I'm going to say nothing new. I'm mostly going to be kind of very quickly trying to sketch the basic idea behind the approach. So there are other approaches to chaos. I will not be talking about them. Let's see, other caveats. So, okay, I think it's worth emphasizing. So nothing I say is due to me, I guess I should say. Right, this is all stuff I've learned from other sources, and in particular, I'm mostly going to be working off of essentially the first chapter of this book that is called Chaos Book. It seems to be, so this is like some online book. It's rather comprehensive, you can say. Tanovich et al. So this is some like 1,000-page book that goes over all of the steps, or it goes over everything I'm going to say, except in much more detail and much more precisely. But in particular, we're going to be thinking about chapter 1, which is pretty simple and should hopefully be simple to follow. So right. So other caveats for kind of this periodic, or the approach we're going to talk about today, is okay. So that really, we kind of want to think about few degrees of freedom. So we're mostly going to focus on the case where it's not necessarily that our phase space has some small dimension, or our space of states has some small dimension, but that kind of the ones that are chaotic, the ones that we care about, are sufficiently few. Sufficiently not. There's not a lot of them. So this immediately kind of throws out the window direct applications to, say, quantum field theory or turbulence or kind of really exciting stuff in chaos. But this is not me saying that these ideas are irrelevant. It's just that I don't think the technology is quite up to handling, truly many body systems. Great. So those are the caveats I can think of right now. There are probably others that will come up along the way, but for now, let me just quickly state what kind of the precise takeaway is going to be. And so what I hope to convince you is that in this framework, or a useful way to approach chaos, is to think about what does time evolution look like in a chaotic system, And so one of the crowning results of this approach is that we can find a precise relationship between the spectrum of an appropriate evolution operator. And so here in, say, Hamiltonian mechanics, we would have an evolution operator that is just taking a Poisson bracket with a Hamiltonian. So this is the evolution operator in classical mechanics, or really it's the infinitesimal generator of time translations in classical mechanics. So this is kind of what I have in mind when I say time evolution. There's some math hidden under, what is this an operator? What space of stuff is this operator acting on? The short answer is it acts on the space of densities on phase space, so that I have some initial configuration that corresponds to some initial points in phase space. So I want to propagate those in time and see what does kind of that density evolve into as a function of time. And so that would be encapsulated by kind of the spectrum of this evolution operator. And so the precise takeaway is that the spectrum is precisely related to, so I'm going to say spectrum again, but I would say maybe more broadly just kind of features or properties of periodic orbits. And so periodic orbit, again, there's no real fancy term here. This is, I have a trajectory that closes under some finite amount of time. So it's just literally a periodic orbit. Often these periodic orbits are unstable. And so they may not seem to be immediately kind of super relevant for things we care about, but I think this takeaway of this relation between periodic orbits and just general time evolution is rather profound. And so this relationship, I think, is cleanly encapsulated by what are called trace formulas or trace formulae. So I think the famous one of these is, okay, hopefully I'm spelling Kutzwiller's name correctly. So here, trace, we're familiar with the fact that, okay, obviously the trace of an operator only cares about its eigenvalues. So certainly we would expect the trace of so the statement will be that the trace of this evolution operator is going to be in some way fixed by properties of these periodic orbits. And so yeah, I think this is the kind of big picture. If you had to take away two sentences, it would probably be this relationship, the fact that trace formulae exist, but also don't forget our local versus global story that is going to be really important to kind of making sense of this relationship down here. So another comment here just about evaluation. I don't necessarily mean this is only relevant for time evolution. You could put, this is also useful for, say, computing expectation values of things you might care about. And so these trace formulae are surprisingly powerful. And organizing in terms of these periodic orbits can lead to, in favorable circumstances, like rather sharply convergent series that lets you extract, pretty non-trivial information about time evolution. So I think some simple examples would be like, you can kind of compute directly from relatively simple starting points say an exact diffusion. You can find an exact formula for a diffusion constant for, say, like some particle scattering in a lattice of hard spheres, say. And so you can write down very simple formulas that are formally exact. And I don't mean formally as in like, okay, formally, but technically there's a bunch of subtleties where it's actually wrong. I mean formally as in mathematically rigorously correct in certain settings. So great. And so the strategy to kind of uncover these relationships is that we're going to play pinball. And so the setup is that we will be doing standard Hamiltonian classical mechanics. As I said, this isn't necessary, but since we're all likely relatively familiar with how Hamiltonian mechanics works, this is a good place for us. And so we're going to have a simple setup of pinball where we have 3 disks. They're supposed to be identical, but they are not. So in general, all of my drawings will probably be pretty terrible. And so these are disks, and we're going to do hard scattering of. So we send in some particle, or yeah, we send in the pinball along some trajectory, and it'll bounce off, and maybe it'll escape, or maybe you could like bounce a bunch of times before you escape. And so, the goal. Actually, let me draw a few of these to be precise. So we can have something like this guy bounces there, one starting nearby, bounces there, and this guy in the middle bounces twice before escaping. And so the goal in pinball is to get the most points, and we get points for every bounce. So we want to maximize the bounces, or the number of bounces, I should say. And so there are all kinds of ways we can soup this up to make it interesting, but we're going to consider the simplest case of perfect reflection. Your transverse momentum gets flipped in direction. You propagate freely in between the different collisions, and so let's see. Hopefully, the setup is reasonably clear. I should also say, please interrupt at any point if you have questions. But yeah, so if our goal is to maximize the number of bounces we want, or we achieve with a particular pinball, then this is already a hint that that periodic orbits are interesting. Because obviously, if you're in a periodic orbit, maybe there's a simple periodic orbit that just bounces back and forth forever between 2 disks, and so obviously you would win because you would get infinite points that you would never leave if you're exactly on that periodic orbit, and so this might be a simple motivation to say, okay, if I want to win pinball, I should find all of the periodic orbits. But now, the sad part of the story is that the periodic orbits, so I'm going to abbreviate periodic orbits because I'm going to be saying it a lot. So periodic orbits are unstable. And by unstable, what I mean is that, so as we can kind of see in this really crude sketch here, that reasonably nearby trajectories sent into our pinball domain can have pretty dramatically different outcomes depending on exactly where you bounce off of. And so for reasonable setups of, say, what is the size compared to the separation between the disks, this will be a genuinely chaotic system. And so these periodic orbits will turn out to be unstable. And so we kind of have this conflicting intuition that, okay, we care about periodic orbits because that's how we win, that's how we can get the most points, but they are unstable, so that trying to actually aim for a periodic orbit, well, I mean, in some sense, if you're coming from outside, there's no way you can do it. But you can ask, how close could I get to getting along a periodic orbit? Can I kind of hug along a periodic orbit for a very large amount of time in order to get the most bounces before eventually leaving? And so I would say that the kind of quantitative measure you might be looking at, or how would you quantitatively measure say the average number of points you would get in a particular pinball game would be to compute what is the escape rate, where we say this is roughly defined by the probability that you're still in play after a time t is something that decreases exponentially, and this is our escape rate.
So David, just to better understand the setup here, would you think of this like you have an infinite collection of pinballs on one side, or you have like a compact area that has like a circle of pinball bumpers, and then you're going in and out of that domain?
So I think that there's a lot of freedom for exactly what you could determine, or like what kind of setup you could consider. So the simplest thing I'm going to focus on is we're going to have 3 disks. There should be of equal size. That's not really that important. They should be separated by some amount, and we'll just put them on the plane, say. We could imagine putting it on a big box or a big corner. Sorry, put a big box around the pinballs or the bumpers. So we put a big box around the bumpers, and we say that it escapes if our trajectory leaves that box. So I guess for an escape rate, you probably want some big area to say that I've escaped from that area. Yeah, hopefully that clarifies.
Yep, perfect.
And so great. So what is our strategy going to be? And this is a strategy, I think, for more general chaotic systems than just this pinball slightly toy problem we're looking at. So the first step is we're going to kind of diagnose or understand and really diagnose what the structure of phase space. So I'm going to call M. M is our phase space. And so here, really, this is a pretty simple step. Is just, okay, can I find some simple coordinates that are useful for phase space, in general? So this is, here we have our phase space. We have 2 initial positions, 2 initial momenta. So this is a 4-dimensional phase space. So being able to kind of efficiently handle a 4-dimensional phase space probably requires a little thought. Obviously, other more complicated chaotic systems will require even more thought. So,
excuse me, David.
Yeah.
Can I ask a question? Should I think the exponential as like an asymptotic behavior?
That's right. Yes. So
okay.
This should really only apply for late t. Yeah, that's right.
Okay.
For large t.
Because you washed away all features about the geometry and all that stuff, right?
Yeah. So I would say that you would probably expect gamma to depend a little, on kind of some of the geometry of like, okay, what are the size of the disks? What are their separations? Okay. Things like that. But so yeah, I would, yeah, certainly a good amount of stuff gets washed out, but there's probably some dependence. So the first step is just, okay, can we find efficient coordinates, or a reasonably simple way to talk about kind of the trajectories in our system? This is just, do we understand what the phase space is? The second step is going to be, a count or partitioning of phase space. So we're going to find a way to kind of chop phase space into little pieces, and spoiler, these periodic orbits are going to be kind of the skeleton around which we organize our phase space. But we're gonna partition phase space into little cells corresponding to periodic orbits, and then once we've done that, then we measure or kind of weight initial trajectories, so we weight them, according to kind of how our initial phase space region, so I'm going to call phase space regions S. So our original phase space region S naught, which is some subset of phase space, kind of evolves into different cells that we counted in part 2. So this sounds really abstract and vague, but the basic idea is that if you send in some trajectory and it gets stuck for a long time, so it starts bouncing around and really kind of spends an asymptotically large amount of time in bumping around in these different things, then what happens is that you're actually going to be kind of very close to periodic orbits for very large portions of your time that you're trapped in. So that in kind of this chaotic region, the periodic orbits are actually dense in the space of trajectories in phase space. And so, you spend a lot of time, either exactly, not exactly on, but approximately close, very close to a periodic orbit. And so that kind of your dynamical features are going to be dominated by the behavior of periodic orbits. And we need to figure out how to weight, kind of how to assign, a given trajectory, its particular periodic orbit that it hugs for, say, 1 million years, and how that affects its observables. And so the kind of observables we'll mostly be interested in will be kind of late time. They could be, late time expectation values. Simplest things are, like above, would be just this escape rate, but there's more general things you could look at. And so the kind of, the big picture here is that, there's something like a very stat mechy feel to this. So that we have kind of, we're trading essentially kind of a late time average it becomes kind of an average over these periodic trajectories. Where these, this average is determined according to these weights that we had to compute previously. And so yeah, I think that's all very abstract. So hopefully it'll get a little more clear as we try to actually carry out this procedure. So, so step one was diagnose. Okay, this is going to be relatively simple. That our phase space is 4-dimensional because we're considering motion in the plane of our pinball. So I think it's an important point also to say that physically we never, in any experimental setup, we never have precise control over, we're never sending in exactly a single perfect trajectory. We're really sending in, some initial density, and so that kind of our initial conditions, we should say, are really specified by some initial density on phase space. So we'll maybe call this a rho naught. And so, right. So we could say, and I think, yeah, for notation, I'll just call the region S naught in M is the region where, the support of rho naught. And so, for classical mechanics, yeah, so for Hamiltonian classical mechanics, we have Louisville's theorem, which says, that the volume of S naught preserved under time evolution I'm just stating this now, but it won't really play a role. In particular, the kind of chaotic formulation we have is independent of whether we're doing precise classical mechanics. And so that's not so important, but it leads to a nice picture of what's really going to happen is we have some initial phase space density that kind of stretches and expands and contracts in different ways and kind of spreads out over all of phase space. And so that's kind of another picture of chaos you can have in your mind, is how an initial very small segment of phase space under time evolution kind of develops these really long tendrils and really kind of spreads around all of phase space. Great. And so for our accounting step, what we want to do is identify, as a 0th order step, is we want to partition phase space. So we want to somehow classify the different trajectories you could have in our system. And so what we do is we try to look for what are the topologically distinct trajectories and so in pinball, this is not so hard to visualize, at least. So in pinball, if we have n bounces before an escape, so if you have n bounces before an escape, then the kind of just the rough ordering of which bumpers you hit is a basic classification of the trajectories, right? So just lists.
Yeah. What do you mean by topologically here?
Exactly. So I mean, I do mean honestly in like a sharp mathematical sense that the right. So these periodic orbits in phase space. So okay, in this context, I just mean topologically in the sense that which bumpers are you hitting? So we have 3 bumpers, and so I could have trajectories that just hit once. So this would be an n equals 1. I could have things that hit twice before escaping. This is n equals 2. But I could also have different trajectories that hit twice. So this is also n equals 2. But if I label my bumpers 1, 2, 3, then I could say that the n equals 1 is labeled by just the single bounce off of bumper 2, whereas this blue trajectory is labeled by 2, then 1, whereas this one over here is 2, then 3. So, I mean, topologically, in this sense that there's a discrete quantification, discrete classification of which trajectory you're on, in terms of which bumpers are you hitting.
Okay, thank you.
Yeah. And again, we can probably also partly see here that the periodic orbits are going to play a role in separating different trajectories. So what separates, say, this n equals 2 versus this n equals 1 is going to be a periodic trajectory that bounces back and forth forever between bumpers 1 and 2. So periodic orbits separate kind of the different classes of trajectories. And so, right. So the kind of the goal here, or the upshot, is we organize our phase space around periodic orbits, and time averaging. So this replacing time averaging by orbit averaging, I guess you could call it. It's probably not a great name, but so these 2 steps will then lead to kind of powerful results in, let's say, late time limit. So for late time behavior, we'll get a lot of mileage out of these 2 things. And so when I say organize phase space, what do I really mean? Well, so let's say we had a picture of phase space, some region here, and I say that this point here corresponds to some periodic orbit. Well, one thing we know is that by understanding kind of what is the linearized time evolution of this what does time evolution look like kind of linearized near this periodic orbit, that'll give us a natural size for a neighborhood that we can then associate to each periodic orbit. So the statement is that we have in our phase space, we have scattered a bunch of different periodic orbits that all have their own tiny little neighborhoods associated with them. And so as we have, you know, some region that spreads throughout, so as we have, you know, some initial chunk S naught that evolves in time and starts developing tendrils and moving all over phase space, it'll start overlapping with these little neighborhoods associated with periodic trajectories. And when you're overlapping with that neighborhood, then you're essentially kind of, this is where you get the weights for describing your average in terms of averaging over orbits, because these periodic orbits tessellate all of phase space. And as you time evolve, you spread out over phase space and you spend some amount of time in these different periodic orbits. So I think to be a little more precise, or, you know, another hallmark of this partitioning, you know, let's try to set up a concrete setting here. So we're going to have these 3 disks. So we're going to imagine a trajectory that starts from somewhere on disk 1, and it can, so this will be kind of parameterized, let's say, so this is disk 1, it'll be parameterized by an arc length and kind of an initial momentum, which you could, we're really going to care about the angle phi in there. So we're going to be looking at starting our pinball, just imagining that it's just completed a bounce off of bumper 1, and we're going to see, okay, what are the different things it could do? Well, the simplest thing it could do is just, you know, bounce away and escape and leave our pinball table. But of course, it could also bounce towards disks 2 or 3 and continue live. You know, you get to live another few seconds before you either escape or bounce again. So in terms of kind of these coordinates, so in terms of the arc length and the angle in which you're shot out, there's kind of different regions where you hit. Okay, this is not drawn well, but something like this. So this is the strip where you go from bumper 1 to bumper 2, and this is a strip where you go from bumper 1 to bumper 3. 13. And so hopefully this picture is reasonably clear that there's some portion of phase space, you know, if I send the particle normally away from the bumper 1, then there's some arc length where you know, you're going to hit the sphere 2 or sphere 3, and so these 2 regions down here correspond to, you know, these regions down here. So one of the difficulties is, you know, visualizing phase space in higher dimensions. So this is, if you've had a good classical mechanics class, this is an example of like a Poincare section, but we're not going to be needing any fancy terminology. So this is, you know, considering our pinball that has just left bumper 1 and it does something. You know, for some region of phase space it hits bumper 3, and for some reason of phase space it hits region 2. Now, I think the really kind of key point here for chaotic systems is that there's really a hierarchical structure hidden in this, in kind of these setups, right? That I could think, okay, what if I don't care about only making 1 bounce, but what if I want to make 2 bounces, right? What if I want to hit 3 and then 2? Well, that has to be some subset of this strip 1 to 3. And similarly, if I wanted to look at a bounce that goes off of 1, hits 3, and then comes back to 1, that would also be some other subset of this 1 to 3 strip. So secretly within this strip of 1, 3, there's another strip that is like say a 1, 3, 2, and then there's another strip that is 1, 3, 1. And similarly over here, right? Similarly, I could bounce from 1 to 2 to 3 or 1 to 1. And so there's a hierarchical structure of the different, topological classes of this phase space. So this hierarchy, leads to, you might say like kind of fractal-like structure or fractal-like phase space. So I think, fractals often come up when folks talk about chaos. And I think this is, part of the reasoning why you would expect such a thing. And so, there are simple things you can do in terms of this partitioning and this counting that yeah. So I think maybe the simple objective might be, I probably should have stated this earlier. So let me just, so as part of our counting, we could say how many topologically distinct trajectories are there? How many topological classes of trajectories are there for, say, n bounces? Then it turns out you get 2 to the n, right? This grows exponentially. So the number of periodic orbits grows exponentially in kind of the number of bounces you're making. And so the fact that it's growing exponentially is related to this kind of global mixing. And so this log 2 here has a fancy name of the topological entropy of the system, which can be defined more generally than the simple setup. But yeah, I just wanted to make sure I mentioned that. But it's really, this topological entropy is telling you about the growth of kind of the periodic orbits. As here, it's kind of like almost like a discrete time evolution because we're looking from bounce to bounce. But very shortly, we will not really focus on that so much. And so, yeah. Now let's get back to, we want to compute something. So how do we compute escape rate, for example? So here we get into kind of the weighting or the measure of our chaotic system. And the idea is really to, if I can compute let's see, after one bounce. So if I escape after one bounce, then I know I'm in the region outside of these two strips. So if my trajectory starts in one of these regions outside the two strips, then I know I escape after one bounce. And so the probability you survive is just kind of the area of the two strips relative to the total area you're starting with. And so you can kind of get the probability by just comparing areas. So let's call this the 1 to 2 strip, 1 to 3 strip. So if I survive after one bounce, then I know I have to be in one of those two strips. So the probability is just going to be kind of schematically the area of phase space at time t over kind of what is my initial volume. And you can generalize this over n bounces by, just summing over all of the areas of the different phase space strips corresponding to a particular n bounce class. So again, these are topologically distinct classes. So I have, 2 to the n different strips for n bounces, and I want to compute those areas. And so there are ways to estimate what this sum is, but I think I'm running a little late, and so I will probably skip exactly how that goes. There's all kinds of fun things you can do here. You can understand like okay. There's a lot of ways to make this reasonably precise that I'm not going to go into, but I recommend you look at the chaos book if you're interested, because I think for our purposes, we can just look at a continuous time formulation and say our escape rate as a function of t, we can just compute as an integral over phase space, over 2 points in phase space, of a delta function actually, let's call this where f sub t is kind of our time evolution map on phase space. So yeah, hopefully this formula is relatively intuitive. The escape rate you can define as just, okay, if I take a point that's initially in my region of phase space, let's say it's on my pinball table, and I evolve it in time, is it still on the pinball table later? That'll tell me, whether or not my pinball has escaped. And so the expectation is that at late times, this should evaluate to something like e to the minus t. But I think the real kind of interesting feature of this expression is that the structure is that, we really care here about the kernel. I'm going to call curly L sub t. It's a function of 2 variables, and it's just this delta function. And so we can kind of schematically say that gamma of t is in some sense, in some kind of a fancy functional analysis type way, the operation of this kernel on some initial density. And then we just say, as a function of time, we care about what does this operator L sub t look like? What does it do? So this is very schematic expression here, so I should write squiggles. And so for continuous time evolution, we're used to writing this in terms of a generator, where, as I mentioned kind of at the beginning, that for Hamiltonian systems, we can think of this generator as the Poisson bracket with a Hamiltonian. And so, yeah, I think since we're all, probably experts in quantum mechanics and understanding in QFT and, how to deal with operators acting on stuff, that we can just kind of say that, at late times, it's the largest eigenvalue of LT that dominates. The kind of time dependence of gamma. And so there are a lot of subtleties, and okay, what function space, why should I expect that I have, a nice set of eigenvalues or eigenfunctions for this random operator I've just thrown at you. So I'm going to ask you to take that on faith. But I think it has been rigorously worked out into what settings you expect, nice spectral properties of this evolution operator. But yeah, so the fact that we can write this escape rate in terms of this evolution operator acting on our initial density at late times, we would want to do something like expand rho sub 0 in terms of eigenfunctions of this time evolution operator, and then just pick out the largest eigenvalue. So this is a long-winded way of motivating that we care about the spectrum of LT. And so a simple way to get at a spectrum is to take the trace of the operator. And if we look back at what our definition of LT was, we have this delta function. So obviously I should set y equal to x and integrate over x. And so that this is going to be something like an integral dx of delta of x minus ft of x. And so voila, we see that periodic orbits have made their appearance in this kind of rather fancy story. And so I think just to end, I'm just going to write down, that this is an integral that clearly prioritizes, trajectories that come back to themselves after some time t. And so we would maybe expect that periodic orbits, where the period of your orbit is some multiple of this time interval t, are going to play a role. And indeed, you can write down an exact expression for this trace in terms of these periodic orbits. So I'm just going to write it down, and then we can stare at it and then probably end, because we should do that. So, okay, so there are a lot of variables in this thing here. So T sub p is just the period of our orbit. This is just the statement that I could repeat that orbit, r times in the given time interval t we have. And then, okay, this determinant, okay, we have a delta function. So determinants often show up with delta functions. This determinant is just completely fixed by the local behavior of the flow near these periodic orbits. And so, yeah, this is an exact expression in terms of all of this data about periodic orbits. So I think the virtue is that if you can find, sufficiently simple short periodic orbits, this will give you kind of a handle in which you can expand to try to evaluate these eigenvalues. And I think there's a lot of really impressive success stories in using these trace formulas to compute interesting observables by including really only 2 or 3 periodic orbits, right? Like you include the smallest, the shortest, 1 or 2, 3 tops. You find those numerically, you plug them into this formula, and you try to extract these eigenvalues. And people have done things like found the say spectrum of helium, quantum mechanically. Once you soup this up with a little quantum mechanics, you find the helium spectrum to 1% for all eigenvalues that are accessible, within a couple of different periods, including 2 or 3 periods gets you, down to a couple of % accuracy in helium. So it's rather impressive, some of the results people have. But yeah, I should probably stop because I've gone a little over. So yeah, hopefully very big picture of what this kind of the role periodic orbits can play in understanding time evolution and classical mechanics. So yeah.
David, can you repeat the example of the helium?
Right. Yeah, I can talk a little bit about that. So what folks have considered is kind of a toy model of helium, where you can consider what's called collinear helium, which is, you can just consider this as a classical mechanics problem. I have, electron, nucleus, so nucleus and other electron, and so so the statement is, okay, so I feel like yeah, all of this has kind of a quantum mechanic-y feel to begin with. So the semiclassical quantum chaos story is that you can, the fact that this looks very similar to quantum mechanics is not an accident, and you can soup it up to really become quantum mechanics. But roughly speaking, the idea is that, there are some pretty simple periodic orbits you can picture just immediately in collinear helium. And when you plug the first 2 or 3 of these simple periods into this kind of a trace formula, you can get the spectrum of helium surprisingly accurately. So,
so basically here
spectrum
the
of
system is including 2 electrons and 1 nucleon.
That's right. Yeah. So this is just some charge 2, Q equals plus 2, really massive thing, right? So we're assuming the nucleus is not moving, the electrons are much lighter. So this is really kind of a 2-particle system and a particular potential that interact with each other, right? So the electrons do feel each other. So the Hamiltonian here would be something like, P1
like 2 electrons in the potential and with the Coulomb interaction with this other.
Exactly. So it's the Coulomb interaction between, so this is like 1 over R1 plus R2. And then there's a 1 over R1 and a 1 over R2. This distance is R. And yeah, so this is a slightly more involved story because you have to kind of add quantum mechanics a little bit. But hopefully I was really just kind of impressed at how quantum mechanical everything felt even before actually explicitly adding quantum mechanics in this chaos story. So I think it's kind of fun. And it, really the starring role is just these evolution operators, right? Somehow it's not exactly a natural thing we think about in classical mechanics, I should say. But it is, really at the end of the day, we should have been thinking about it, because really what we have is some initial density of configurations that we care about, and we care about what is that density of configurations do at late times where we need to time evolve it.
So the thing I asked, because I confused, like, where can we put the 8 bar into this classical to have the correct spectrum? That's I really confused.
Yeah. That's right. So there you need to do some semi-classical magic.
Okay.
So really the kind of correct way to kind of work with these traces is to really like Laplace transform. You turn this delta function into exponentials, and then kind of the weights of those exponentials get a semi-classical contribution. So that's where your H bars come in, is kind of you add in some kind of quantumness to the weights in this Laplace version of the formula.
Okay. Makes sense.
And I mean, it is kind of, it's very similar to kind of the Bohr-Sommerfeld kind of story, right? Where kind of I have phases determined by the action of these classical paths, possibly up to some discrete shifts. So I think there is a really, really robust story of how to generalize this classical trace formula to quantum mechanics. But certainly both beyond my scope of this talk and my understanding of the material. But
thank you.
Yeah, I think it's super interesting.
Yeah.
So the periodical orbits appeared because you took the trace, right?
Exactly. Yeah, it's kind of silly how they
Right.
showed up here, right? It's just, oh, I'm taking a trace, so of course I care about periodic things.
Right. So and the trace because you care about the eigenvalues.
Exactly.
Right. So by definition, then periodic orbit is the one that comes to itself after some time evolution, which is by definition is the eigenfunction. So it shouldn't be surprising to find, since you're looking for the eigenvalues, it's not surprising to find the eigenfunctions as the answer. And periodic orbits classically, if you go to quantum mechanics, then they, because of the uncertainty principle, it may not match precisely. So that will, after some time t, you may not come to exactly the same point, but there is some uncertainty. So that will promote to the wave function, which is the eigenfunction of the Hamiltonian. So I think I'm missing something here.
Right. So, I mean, I agree with your assessment that, okay, really, I think the kind of technical upshot is just that, okay, we need to care about what is the time evolution operator in classical mechanics, and we care about the spectrum of that operator, so we compute it by taking the trace. And things that are periodic are what show up in that trace. So I agree that's a very, that's like a one-sentence summary of what happens. But it's still, I think that's still a slightly non-trivial fact in that, the fact that this integral is determined entirely by all of these local features of these periodic trajectories, and it's an exact statement that relates it to the entire spectrum of the time evolution operator is, I think there's a lot to unpack there. And I think the one thing I probably didn't emphasize quite as much is just the utility of the actual kind of expansion, like the actual kind of computational abilities that this formulation gives you, right? So I think it's important to notice that we separate between a single period and kind of a repeated period, right? Where in a given time interval t, I could still have a periodic path that repeats a simpler fundamental cycle twice in that time period rather than just the full time period. And so,
and I was curious whether this R parameter that you're summing over, why it doesn't take negative values? Why I'm not summing also -1, -2?
Well, because then, so I mean, really, I think the idea here is that we need RT to be a time interval, right? RTP. So we're completing. So
yeah, but I mean, it's the same time interval, but you went the trajectory in the opposite direction. So you can have, if you interpret it as a winding mode.
So I would think that would be classified as just a different periodic orbit, right? I would separate those two periodic orbits as different classes of orbits, right?
Although you go from 1 to 2 and 2 to 1, you'll say it's a different orbit because I go in the opposite direction.
So, okay, there's also the fact that there's a zero mode. So kind of where you start on the orbit, that's where this factor of TP came out.
Okay.
So I think that would probably account for this factor we're talking about here, right? So if I consider an orbit between, disks 1 and 2, that goes back and forth here forever. Yeah, you have to be a little careful to not overcount your orbits, whether you start down here or you start up there. So yeah, you have to be a little careful, and that's where some of these factors come in. Why this M over here has a tilde is because there's some subtleties there I don't want to talk about. But yeah, I think you're right in that it is such a simple idea that it's kind of it seems a little trivial, but
no, yeah, I agree. When you started and you said, oh, it's going to be determined by the periodic orbits, I say, why? But then the more I think about it, it's kind of obvious. But I wasn't expecting that at the beginning.
Yeah, exactly. And so yeah, I think really the like in this game of pinball, the virtue is that you can set up really systematic, highly convergent expansions in terms of these orbits. So in pinball, you can just look at it and say, okay, I know the simplest class of periodic orbits here, so let me just plug in and what kind of escape rate do I get? And including 3 orbits, you get like 3 or 4 digits of precision. So at least, I think. So somehow the kind of longer, the convergence in terms of which periodic orbits you need to care about is both a blessing and a curse, in that there's a lot of them, but they're weighted relatively weakly, I think, is morally how it turns out. But yeah, I guess.
It's also.
So
okay, Steven.
yeah, I just wanted to say thank you again, David. So I'm going to stop the recording, but virtual round of applause.